All right, this is lesson 1.9 of our Pre-Calc 12 class. Unit 1 is called Functions and Transformations. Lesson 9 is called Composite Functions. What we're going to learn in this lesson is what is a composite function and how to evaluate composite functions. So when we say composite functions, what we mean is, in the last lesson we talked about adding and subtracting and multiplying and dividing different functions. So now, what if I put a function inside of a function? So normally the input of a function we call x. What if the input of a function is just another function? Well, this is how it would look like. So right here we have f of g of x, is how I would say that. And notice that normally we would say f of x, but instead of x inside the input for f, there is now a function, g of x, as the input for f. Crazy, you can do that. My understanding is that none of you know who Leonardo DiCaprio is. So if I made an Inception reference, no one would get it. But you can Google it. Anyways, so this means we're putting a function inside of a function. The other way we can write it is like this. F of g of x is how you say that. G is the inside function and is inside of f. Notice that this notation looks very similar to multiplying. It's a circle that's white on the inside, not a black dot. Black dot would mean we're multiplying together, but the circle that's white on the inside or hollow or open means we're putting a g inside of f. Okay, so here's a bunch of examples here. So here's five example functions that are all different parent functions, and we can compose them any which way. So if I say f of g of x, f is the outside function, is equal to the square root of x. G is the inside function, it's equal to 2x minus 3. So we're going to take the inside function, the expression, and that expression is going to go into the outside function. Wherever you see x is going to go out, and 2x minus 3 is going to go in its place. So the square root of x becomes the square root of 2x minus 3. Again, 2x minus 3 is the input function, and it's going inside of the square root, which was the f function. Example C, instead of putting g inside of f, we're putting h inside of f. So this is going to be the square root, and then our input, x, is going to be replaced with the h function, sine of x. So f of h of x would be the square root of sine of x. Sine of x goes on the inside, square root goes outside. Now example B, if we flip this around, instead of f of g of x, if we do g of f of x, we're going to say, okay, f is the input function, and it's going into g. So we're going to take f, which is the square root of x, and we're going to put it into the g function wherever we see x. So instead of 2 times x, it's going to be 2 times the square root of x, and then of course minus 3. So that's going to look like this right here. Take a moment, look at the rest of these, see if you can't make sense of them and how I got to those answers. I try my best to color code. One to notice is maybe example E, we're putting a function inside of itself. Totally fair game. So I'm going to take 2 of x and make that my input for the x. So if I replace the x with 2 of x, I get 2 to the power of 2 to the power of x. Power to a power. Interesting. All right, and then another one to notice is the sine of x. Only because sometimes I write sine x, and sometimes we write sine and then put the x in the brackets. Technically speaking, adding the brackets is more proper. But sometimes in math, when you get really into trig, you just get lazy and you don't put the brackets. And it's just implied that x is the input. If that's confusing, I'm really sorry. Just let me know, and I'll make sure I have my brackets. Anyways, take a look at those examples. Now's your chance to pause the video. We're going to move on. All right, what if for funsies, let's say, we put a function inside of a function and put that inside of another function. Well, here's how it would look like notation-wise. We could say f of g of k of x, and we could write that like this, as in k of x is the input for g of x, and then g of k of x is the input for f. Another way to write that with less brackets, or actually the same amount of brackets, no, it's less, is like this, f of g of h, as in h goes inside of g, and then that goes inside of f. And then given our examples from before, if we did that, we put 2 to the power of x in place of the x on the g function, because k goes inside of g. So we'd have 2 times 2 to the power of x minus 3, and we'll take that and put it inside of the f function. So the square root of 2 times 2 to the power of x minus 3. Aha! Function inception. Again, Google it. It's a good movie, kind of. Alright, so one quick note. Function composition, or composite functions, have an input-output relationship, and there are, I think I have a typo on these instructions right here, but the important thing to note is that putting g inside of f is not going to give you the same answer as when you put f inside of g. Sometimes it might, and that's sheer coincidence, but in general, don't count on it. Oftentimes, f of g and g of f will give you different results. And we could do that example here, but we've already done that on the back slides. Example A and example B are just that. If I put g inside of f, I get one expression. And if I put f inside of g, I get a different, similar, but different expression. Those two are not equal. All right, so again, we're going to talk about domain restrictions. When I put a function inside of a function, the domain of f is not necessarily the domain of f of g of x. F of g of x, the composed function, its domain is limited by the function g of x. And so to highlight that a little bit more, for g of x, its domain is any real number. That's what this says right here. X is an element of all real numbers. I could take any number and put it into g of x. So any number is in the domain of g. However, g is defined as being the input squared, or x squared. So if I take any of these numbers and I square them, what's going to happen is I'm going to only get all the positive numbers. Because any negative number squared is positive, 0 squared is 0, and any positive numbers also, when it's squared, is also going to be positive. So the range of g is any number greater than 0, or equal to 0. So then the range of g would be any x value greater than or equal to 0, where x is the element of all real numbers, or x is any real number. But now the range of g would be the domain for g of, the range of g would be the domain of f of g of x. So whereas maybe x, I can put anything in x, f of g of x is limited to just positive numbers. Okay. Plus all the domain restrictions that are inherent with whatever f is anyways. But that's that. More food for thought. Some example problems, evaluating composite functions from a graph. If I want to evaluate example A, f of g of 3, I'm going to take 3 and use it as an input for the g function. So on our g graph, I see that 3, -1 is a point on that graph for g. And so when I put 3 in for g, that means -1 comes out. So that tells me that f of g of 3 is the same thing as f of -1, because g of 3 is -1. So then I'm going to go to the f function on the graph. I'm going to find the x when the x value is -1. And I see that the point -1, 5 is on the f curve. So when I put negative 1 into f, 5 comes out. So f of negative 1 is 5, which means f of g of 3 is also 5. We can continue that pattern for example B. We're going to do g of f of 3, which means we take 3 and we put it into the f function. We do that, 1 comes out. So g of f of 3 is equal to g of 1. We'll take 1, we'll put it into the g function, and we notice negative 5 comes out. So our answer again, g of f of 3 is negative 5. Last example, we're going to take f of 3. So we're going to put 3 into f and run it through twice. When I put 3 into f, 1 comes out. And so f of 3 is equal to f of 1. Then I'll put 1 into f. When I put 1 into f, 3 comes out. So f of 1 is 3, which means f of 3 is still 3. So that one just came full circle. We turn it into 1 and turn it back into 3. So these are examples of evaluating composite functions from a graph. Here's an example of doing a similar activity, but from the function notation with an expression. And we're not given a value for x, we're just given x. So if I do example A, what we're going to do is we're going to take g of x and put it inside of f. G of x, this trinomial, is going to replace x in the f function. So instead of 3 times x minus 1, it's going to be 3 times that trinomial minus 1. And we can distribute the 3 and collect like terms and get a simplified expression. We could put f inside of g, so that means the 3x minus 1 is our input for the g function. And anywhere we see an x, we're going to replace the x's in g with 3x minus 1. So instead of x squared, we have 3x minus 1 squared. And instead of plus 3x, we have plus 3 times 3x minus 1. And then plus 7. And we can square the binomial. That's a little box method I did in my head. We can distribute the 3, and then we can drop the brackets and collect like terms. We get a simplified expression like this. Again, notice f of g of x is not equal to g of f of x. These are different expressions. Alright, so we can also evaluate specific numbers in composite functions. So if I wanted to find f of g of 3, I'm going to take 3 and put it into g, whatever the output is. Let's see here. If I put 3 in for g, I get 3 squared plus 3 times 3 plus 7. That's 9 plus 9 plus 7, which is 25. So f of g of 3 is the same as f of 25. So I'll take 25 and put it in for x in our f function. So 3 times 25 minus 1. And simplify. We get 74. Now I can do g of f of 3, which is similar to a, except 3 goes into f first and then goes into g. I'd write that because I would say, all right, f of 3 is going to be 3 times 3 minus 1, which is 8. And so then g of f of 3 is equal to g of 8. Well, I'm going to put 8 in for g, so we get x squared plus 8 squared plus 3 times 8 plus 7, we get 95. Example C, we can do similar, except we're putting 3 into f twice. So 3 goes into f, we get 8. 8 goes back into f, we get 23. Alright, so some takeaways here. We know how to understand composite functions. We can write composite functions as an expression, and we can evaluate composite functions or composed functions from a graph and from function notation. And then we're still continuing to build our understanding of domain. Domain, as I like to call it, is who's invited to the tea party. And if you're wondering, the answer is yes. Yes, you are in Precalc 12, and so you are invited to the tea party. If that means no sense to you, don't worry about it. I'm just being silly.